So let's get started here. So today we're just going to go over some kind of introductory stuff, kind of give an overview of building analytics applications, the kinds of things you need to talk about, the things that you sort of consider and go over. I'll do a brief introduction to MapReduce and Hadoop. Just hands up, how many people know what Hadoop is? Okay, so that's everybody. Awesome. And how many people know exactly what MapReduce is? Okay, all right, so about half. Okay, so after we go through that, then I'll do some kind of introduction to cascading and PyCascading and kind of go over what the differences are and all that kind of stuff. So first, a little bit about me. So who am I? Like, why am I here? And what makes me qualified to do something like this? Well, I've been doing some of this stuff for quite a while. I first started working in analytics in finance in 2005. It was kind of a different type of world then, so there was no such thing as Hadoop. The MapReduce paper had not really taken off. Everyone was working with like giant hardware. If you remember those giant Sunfire E15Ks, which are like $1.2 million a piece, and they were just these massive machines, and it was incredibly expensive and not terribly reliable, and everyone was moving over to these distributed cluster computing systems. So in 2009, I moved to Toronto, and I got a job at Polar Mobile. I was initially hired to do some analytics development. I ended up, kind of working in engineering there. And then finally, this past fall, I made the move over to Kontagant, where I'm now a yellow elephant tamer. So I deal with kind of the data processing team at Kontagant. We deal with all the data collection, data processing, kind of all the reporting that goes along with that. So we deal with quite a bit of data, and just to give you some sense of scale from like where I'm coming from, and my frame of reference. So we've been around since 2007. Blah blah blah. The really important things here is that we process about 6 billion events a day. We're tracking about 200 million users per month, which is a decent chunk, and we did over 1 trillion events this past year. So we're dealing with some sizable amount of data. We're not just kind of doing a couple thousand requests a second. We're doing tens of thousands of requests per second per node in our network. So it's a fairly large volume. So let's start with what is analytics. So analytics is just making sense of your data. That's it. But there's a little bit more to it than that. There's you kind of have to form an understanding and then take some action as well. So it doesn't matter if you understand what's going on if you can't do anything about it. So here's a good example of something that a business would really care about, which is kind of a lifetime value curve for your users. I want to know what the value of that user that I'm bringing to my system. I've paid some marketer to bring them into my system. I want to know if I'm making a positive return on that or not, right? Is this a really cheap source for me to keep getting valuable users into my system, or is it really expensive, right? So businesses have all kinds of questions like this, and traditionally these tools weren't available to them. These were kind of relegated to industries like finance, where they had a lot of money to throw at these sorts of systems, and they could kind of do this stuff willy-nilly because they had tons of money, and other businesses didn't really have the option of getting this much information, and now we kind of do. So we have a lot more flexibility these days. So in terms of data at Kontagant, this is how we collect our data. So we'll be building kind of a little sample application that'll look at kind of log data like this. This particular one we're looking at is actually an internal log format that we produce called KT-raw. It's kind of a chopped down version of like an Nginx log file. It kind of saves space, and it's a little easier to look at. We've kind of removed some of the superfluous details, stuff like that. And it's also been broken up some specific way. We have a number of different message types. So it's really hard to see that, but there's the second column there is actually a message type. So a lot of these are like custom events, which is that EVT message. There's APAs, MTUs. And we feed this through our system into a real-time system. So we're kind of constantly scraping all these logs from all of our servers and sending them to a single stream and processing them from there. So this is the kind of data that we deal with, and this is kind of what we'll be looking at. But before we do that, let's let's take a look at actually what MapReduce is, and get an understanding of what it actually is. So 2004, Google published the paper, MapReduce Simplified Data Processing on Large Clusters. No one noticed for a little while, and then everybody noticed. So Doug Cutting at Yahoo kind of went, oh, this is really interesting. Hadoop sort of came about from that whole thing. Fundamentally, it is inspired by functional programming, and that's why it uses some of the same terminology, but it's not the same thing. It's very different. And so it's really a computational model for dealing with distributed systems. So it's a way of thinking about how you do your computation. That's it, nothing more. It's kind of a two-phase system. So map takes your input, divides it into subtasks, and those get pushed out to all your nodes, and then reduce combines them to produce an overall result, right? So in the old world, we'd kind of push all of our data that we needed to look at to each node, run our computation there, and go from there. Hadoop world is kind of the reverse of that, where you're pushing your computation out to where your data lives and running it there, and then sort of collecting all the results at the end. So that's MapReduce. And so Hadoop was built to sort of make a MapReduce framework. It's based on the Google MapReduce and GFS white papers. So HDFS, which is the Hadoop distributed file system, and is an important part of this data locality, is that it's based on the GFS white paper. So yeah, so people say Hadoop, and people think, oh well, it's this specific clustering software, or it's HDFS. When they say, oh, I'm putting it on Hadoop, no, you're actually putting it on HDFS. Or they say Hadoop, and they actually mean the ecosystem around Hadoop, which is HBase and all these different things. So Hadoop is like a very loaded term, and I can ask if everyone knows what Hadoop is, but I think there's probably 6 different answers in the audience of what they actually think Hadoop is. So in terms of what we care about the actual MapReduce part of Hadoop for this talk. So MapReduce. Humans don't think of MapReduce. It's not really a natural way of thinking about your computation. It's okay, I have to do this little thing, and then I break that up, and then I send it over there, and then I have some way to combine it, and then I produce a final result from that. And I may do that in 2 or 3 stages, and it's not at all how any of us think about actually solving a problem. We kind of think through logically what we have to do, and then we'll go, okay, now if I wanted to make this on MapReduce, I'd do this, right? So you're kind of mapping the way you think about your problem into the way that MapReduce deals with problems, and then back and forth, right? So it's, it solves this problem, but it's not kind of, a real natural way for you to do that. Fortunately, a bunch of people came up with all kinds of options that are a lot more natural, that kind of deal with the way that humans think about things. There's Hive. How many people are familiar with Hive? Okay, a few. So Hive is this SQL-like query language. So it's kind of this declarative style. Write a query. It actually analyzes your query, does this SQL-like thing where it goes, okay, well, this is a query. Now I need to figure out how I execute this query. And it comes up with a plan of how to execute the query, and that plan gets translated into MapReduce jobs. And that actually produces a bunch of MapReduce jobs that run in your cluster. Pig is a very similar thing with syntax that's not really similar to SQL. So it's kind of its own thing. And finally, with the thing we're here to talk about today, which is cascading. So cascading is kind of a flow-based model. So instead of thinking about things in terms of like run a query, it's still sort of this kind of imperative thing where you're like, do this, then do this, then do this, then do this, right? But it's a data flow, right? Which is how we all think about dealing with data, right? I do this thing, and then I do this thing on the next step, and I do this, and I split it here, and I do this other thing, et cetera, et cetera. So it's a much more natural way of dealing with the problem. And like Hive, it'll be compiled down to MapReduce. So they kind of fall into 2 different models here, the declarative and imperative, but not directly MapReduce. Okay, so flow-based computational model. It's actually not explicitly tied to Hadoop. So when we talk about cascading, it's actually a framework for doing computation. That's it. Everybody runs it on Hadoop and uses it that way, but it's actually not at all tied to Hadoop. It takes your flow diagram and it'll actually produce a MapReduce job from it. So it's kind of this separate thing, but it's most useful in the context of MapReduce. And Chris Wenzel, the guy that actually wrote the original cascading library, actually says, don't actually use the raw APIs. They're written in Java. They're not nice. Don't do this ever. Use some DSL, right? And there's a bunch of DSLs on the language. There's Cascalog, which is one of my personal favorites, which is like a data log clone in Clojure. Scalding, which is the Scala bindings for cascading. Lingual's a newer thing from the cascading guys. We won't talk about that, but it's like a actual SQL 89, I think, implementation on top of Hadoop, which is kind of cool. PyCascading, which we'll talk about today, and cascading.jruby, which I've never used. Might be good, might not be good, but yeah, we'll see. Cool. So, and this is a flow down here. So we have a bunch of these operators. They're connected together. They can have kind of branches off to the side. And everything is connected together. So this is kind of the diagram of how the flow works. But we need to get data in and data out of this flow. And that's done through taps. So they kind of start or finish your flow. And basically, you're just producing a tuple stream. That's it. So you take some source of data, which is this text, this LFS thing, which is local file system source. And you say, this is the source of my data. And the scheme tells you kind of what the input format is. So you can have an input format for just a simple text line, which will give you a string from that file. Or you can have something like a protobuf reader, which is something we use very often. And so it just kind of tells the system how to either input or output or where to input or output the data and what format to put it in. Excuse me. So you can also see here that there's actually no wrapping here for the PyCascading user. Text line is actually a Java class in this case. So this is all in Jython. And it's not very nice. So it looks a lot like Java because it is Java. And it's OK because this part of it, the taps themselves, are actually not all that complicated. So yeah, the API is kind of passable here. But it kind of needs some work. And the other nasty part here is that there's no actual documentation about this stuff other than the Java documentation. So unless you know how Jython works and how the Java interop works, and you can read the documentation for the Java APIs, you'll have no idea what's going on here. So just a heads up there, you won't find that anywhere. But if you've already worked with cascading somewhere else, it'll all make sense because you've done this dozens of times. So once we produce some data, we want to do some work. We want to do something useful, and we do that with operators. So operators transform your tuple stream. So one example here, this is like a sample operator from my sample code that just parses a log line, right? So we have this tuple stream coming in from our source now, which is a one tuple, and it's just a string. Well, that's cool, but it's not really useful. I actually want some semantic part of that string that I actually care about, right? And probably 2 or 3 of them. So in this case, we're actually extracting the API key that made the request, the message type, because we're actually going to do a little kind of click attribution here. So we're going to match up, someone who took some action and, making sure that the result of that action also followed through, right? So someone who clicked an ad, we're going to make sure that they followed through on that action and actually did something with it. So to do this, we kind of need to know what messages to look at. And in our system, they're called APAs and UCCs. We'll see that on the next slide. And so we need to kind of keep track of that. And the query args are where all the actual key values are, right? All the data pairs that we want to look at. So these operators, in this case, these maps, you produce 1 or more tuples from this. So in this case, I'm returning. So this is kind of a 1-to-1 mapping from where I started to where I'm going. So for every input tuple, I'll produce 1 and exactly 1 output tuple. If I had a loop here with a bunch of with a yield in it, I could produce a 1-to-many. So I could take in 1 input tuple and produce a bunch of output tuples, which is useful if you have like a bunch of values packed onto a single line, say. So you can iterate over some values on that line and produce a bunch of output tuples that way. So it kind of takes your stream that's going this way and turns it on its side, right? So that's how you do those things. The thing at the top there, those key, type, and args, are just some names for the tuple that's produced by this system. So normally, you can keep track of the tuples by their index, but it's also good to have names in your tuples so you can reference them later. So that declares that the 0th position is key, the first is type, the second is args, and that's what we actually return down below. Yeah, and there's other types of operators as well. There's a bunch. The two that we really care about for this is kind of maps and filters. Filters kind of may produce 0 or 1 tuples from an input tuple. So basically, you can take a bunch of inputs and kind of filter out what you need. And they look a little different from these. But we'll get to that in a second. And the other part is that, that tuple.getString, that's actually returning a java.lang.string there, which is not a Python string, unfortunately, in Python, and is really annoying. Because if you print it, it'll print exactly like a Python string. You poke at it, it kind of looks like a Python string, and it's not actually a Python string. So you run stir on it, and everything will work fine. But it's one of those gotchas that you kind of have to have worked with it already. OK. All right, so I'll kind of speed this up a little bit. So from here, we're going to actually look at some filters. So they're a little different. They're kind of like a predicate. So I just say, I return a truth value, this input tuple, whether you should keep it or not. So I say, well, I want the UCCs, which are those clicks on ads, and the APAs, which are those install messages, right? So I'm looking to attribute a click on an ad to an install of an application. And I kind of filter those out. It's simple. It's kind of the inverse of the Java API, so just watch out for that. But this one makes much more sense. OK, and now a flow. So now we have to put everything together and kind of pipeline everything together. And we can see we can do a join here after we've kind of taken our pipeline and split it. So on the part here where you see the APA pipeline and UCC pipeline, the pipeline has been split. So we actually read the input only once. We split it into 2 tuple streams, process them separately, filter out only the parts that we care about in each part, and then we do this co-group, which is an inner join, and join them back together, and only keep the fields that we care about. That's those underscore characters, I'm throwing those away, and then only retaining that set of named tuples. And finally, I pipe that to that output flow that we looked at, that output tap that we looked at earlier. The syntax is a little weird. Use this pipe character. The guys at Twitter liked it. I don't know why. It looks really weird. And the join is that and character. I mean, it would be a lot nicer if it didn't require all these function parameters, but it just looks weird the way it is. But it is what it is. And finally, you just run it, and that'll produce a bunch of flows and everything. Cool. I'm told I don't have time for questions, or do I have time for 1 or 2?
I've got time for 1.
1?
All right. Pick someone. What do you want me to bring?
Ooh.
It's up to you. It's your talk, so.
Here.
You guys can all go up to him after and barrage him with your questions.
Yeah.
But.
So my question is, how does cascading compares to alternatives such as Storm or Spark streaming?
So I only heard about Spark recently. I actually don't know a lot about Spark. Spark looks really, really cool, and I need to put some time aside to look at it. It seems to be kind of in the same vein, so they're kind of similar anyway, so they do a similar thing. So it's something I definitely need to look at. In terms of Storm, Storm does something completely different. Storm does real-time event processing, so it processes an event stream without doing this batch-based. So this actually produces a flow that's a batch flow.
Oh,
right?
I see.
So everything ends up as a MapReduce job, which is this batch-based job system.
Right. It just looks like a lot.
It looks like a data flow because that's intuitively what's easier to deal with. But in the reality is it's still a batch system.
Okay.
It doesn't have to be a batch system. It compiles down to MapReduce, which is batch. So that's the reason for that.
All right, thanks very much.
Thanks.